These are the revolutionary manufacturing technologies that transformed 16th century naval cannons from crude blacksmith hammering to precision industrial casting, taking accuracy from 50 meters to over a mile in just 3 decades. What you're about to discover isn't just the story of better weapons, it's the birth of mass production itself. Picture the earliest cannons if you can. They weren't the sleek bronze barrels we imagine, but crude affairs that Sussex historian Thomas Walker Horsfield described as mere cylinders fixed on sledges, sometimes composed of iron bars, laid side by side like the staves of a cask and held together by iron hoops. Yes, the very same technique used to make wine barrels. In fact, that's why we still call this part of a gun the barrel today. These hoop-and-stave cannons were essentially oversized beer kegs with gunpowder inside them. These evolved into the massive bombards that preceded the Bronze Revolution, still crude, but powerful enough to breach castle walls. But by the 1540s, something extraordinary had happened. Master gunfounders were casting single-piece bronze cannons weighing nearly 3 tons, capable of hurling 32-kilogram iron balls over a mile. The transformation wasn't gradual. It was a technological revolution that changed the balance of power on every ocean. The breakthrough came in the foundries of northern Italy, Flanders, and Nuremberg during the 1420s and 1430s. European cannon founders finally mastered the art of casting bronze pieces that rivaled the largest wrought iron bombards in size. But mastering bronze wasn't simple. The alloy was prone to internal cavities and what metallurgists called sponginess. The solution required rethinking everything about how metal was melted, molded, and cooled. The secret lay in the recipe. Analysis of cannons recovered from Henry VIII's flagship Mary Rose reveals the precise formula: about 1 part tin to 20 parts copper, roughly 5% tin content. The tin that strengthened these bronze guns came primarily from Cornish mines, traded across Europe for centuries. But here's where it gets fascinating. The cooling process created an unintended gradient. The breech, buried deep underground in the casting pit, stayed insulated longer than the muzzle. This caused tin to migrate toward the breech during cooling, making that critical pressure-bearing section stronger while leaving the muzzle more brittle. It was accidental metallurgical engineering that actually improved the cannon's performance. The casting process itself was an industrial marvel. Workers dug pits like wooden barrels sunk into the ground, with wooden staves held by iron hoops and adjustable platforms. For the mold, they built up clay around a wooden spindle, winding rye straw rope tightly, then adding inch-thick clay layers. A small fire beneath the spindle slowly dried the model as craftsmen used templates called strickles to shape the barrel's profile. The same bell founders who cast church bells across Europe turned their specialized bronze working skills to artillery, bringing centuries of precision casting expertise to cannon manufacturing. Then came the most dangerous moment: the pour. Molten bronze at over 1,000 degrees Celsius flowed from furnaces into vertical molds. Cannons were typically cast breech down, putting the molten metal under pressure at the chamber, the most critical point. Workers used wrought iron fixtures called chaplets to center the core, creating the hollow bore that would be precision machined later. This wasn't just craftsmanship, it was early industrial engineering. The Venice Arsenal, which economic historian Frederick Lane called perhaps the largest industrial plant of that time, employed 16,000 workers at its peak in the early 1500s. They could apparently produce nearly 1 ship each day, complete with bronze armament. When King Henry III of France visited in 1574, the Venetians deliberately led him through every step of warship construction to demonstrate they could replace any battle losses immediately. But the real revolution was happening in the English countryside. In 1543, in a workshop in Buxted, Sussex, an ironmaster named Ralph Hogge achieved something unprecedented. He cast the first iron cannon in England. Working with French-born cannon maker Pierre Bode and funded by parson William Levet, Hogge cracked the code of casting iron artillery. Here's the paradox that makes this story remarkable. Parson Levet was literally a man of God, charged with praying for peace, whose business thrived on the prospects of war. By 1543, this Sussex clergyman had become England's leading supplier of cast-iron muzzle-loading cannons. The Wealden iron industry that grew from this breakthrough would dominate global cannon production for over a century. The technique of casting iron guns vertically in stave-lined pits, pioneered in the Duchy of Jülich in 1539, found its perfect home in the forests of Sussex and Kent. England's abundant timber fueled blast furnaces, while local iron ore provided raw materials. The impact was immediate and global. Cast iron artillery was dramatically cheaper than bronze, perhaps one-third the cost, making it accessible to merchant vessels and smaller navies. As one contemporary observer noted, cast iron ordnance quickly made its way onto the decks of commercial vessels before state navies fully adopted it. Private enterprise was driving military innovation. The Mary Rose, which sank in 1545 with 91 guns aboard, gives us a precise snapshot of this transitional moment. Her artillery included 4 types of bronze muzzle loaders: cannon royal, demi-cannon, culverins, and culverin bastards. These weapons ranged from 1.4 to 2.7 tons in weight, with lengths between 2.6 and 3.7 meters. They fired cast iron shot ranging from 65 to 210 millimeters in diameter, weighing from just under a kilogram to 32 kilograms. The shortest firing range was 250 to 420 meters horizontally, but by elevating the muzzle, the longest range guns could reach 1.5 statute miles. One crucial innovation often goes unnoticed: the invention of trunnions. These cylindrical mounting lugs, cast integral with the barrel just forward of the center of gravity, provided the principal attachment point to the carriage and a pivot for adjusting vertical angle. Charles VIII of France's 1494 Italian invasion had demonstrated the devastating mobility these trunnioned cannons provided, revolutionizing siege warfare. By the 16th century, most European founders were casting these lugs in the shape of leaping dolphins, with similar decorative fixtures on the breech. It sounds merely aesthetic, but trunnions revolutionized artillery mobility and accuracy. The competition between bronze and iron sparked international industrial rivalry. Spain's royal foundries at Medina del Campo, Malaga, Barcelona, and Seville could barely produce 3 dozen average-caliber guns per year during the first half of the 17th century. Meanwhile, England, the Netherlands, and Sweden each operated multiple foundries, casting 100 to 200 cannons annually. Northern Italy, Flanders, and Nuremberg remained famous for the finest bronze guns, while England and Sweden dominated the market for cheap, high-quality iron cannon produced in massive quantities. The technological challenges were immense. 16th-century cannon founders had no way of predicting internal stresses or measuring metallurgical properties. As one modern analysis notes, the design of bronze artillery in the early modern era is clearly a case of developing technology unsupported by a well-articulated theory. They worked through trial and error, catastrophic failures, and gradual refinement. Safety was a constant concern. Artillery crews faced as much risk from their own weapons as from enemy fire. Cannons could split or explode without warning, often killing nearby crew members. Some founders secretly repaired flawed cannons with screws rather than recasting them, a dangerous shortcut that archaeological evidence shows was more common than previously thought. Yet the impact extended far beyond Europe. In 1513, a Javanese fleet attacked Portuguese Malacca with much artillery made in Java, for the Javanese are skilled in founding and casting, and in all works in iron. The technology had spread globally with local variations. 16th century Javanese cannons ranged from 180 to 260 pounders, weighing 3 to 8 tons, with lengths between 3 and 6 meters. The transformation from hoop-and-stave barrels to precision-cast artillery represents one of history's great technological leaps. It required advances in metallurgy, industrial organization, quality control, and manufacturing processes that wouldn't be seen again until the Industrial Revolution. These weren't just better weapons, they were the products of humanity's first experience with true mass production. The foundries of 16th century Europe didn't just forge cannons. They forged the future of industrial manufacturing itself, creating techniques and organizational methods that would echo through centuries of technological development. These Sussex cannon foundries would arm the ships that defeated the Spanish Armada just 14 years later. From the wine barrel construction methods of medieval blacksmiths to the precision engineering of Renaissance foundries, this was the moment when human craftsmanship evolved into something entirely new: industrial technology that could reshape the world. But sometimes, engineers don't always get it right. Click the video on screen right now to hear the story of how an engineering failure caused an entire ship to sink and triggered a government cover-up.